Question number 3, this is the beginning of the organic structured questions. So we are told that there are 6 molecules. They are all structural isomers. Structural isomers defined as molecules which have the same molecular formula but different structural formula for obvious reasons. C4H8O, 4 carbon, 8 hydrogen and 1 oxygen. A, B and C give you orange precipitate with 2,4-DNPH. So A, B and C has ketones or aldehyde. So they will give you a positive orange precipitate when they condense, when they undergo condensation with these 2,4-DNPH. Only A and B give a brick red PPT, so only A and B are going to be aldehyde because only the aldehyde can react with phalanx or toluenes. When it reacts with phalanx, which is blue solution, you get a brick red PPT. This brick red PPT is copper +1. You're going to get copper 1 oxide. That is going to be Cu plus and O2 minus. So you're going to have 2 of that Cu plus. So that thing there is Cu2O, copper 1 oxide there. And what do they want? They want skeletal formula, my favorite of all time. There are 4 carbons. So we're looking at 4 carbon aldehyde and 4 carbon aldehyde. And there's no other information given. If we look at aldehyde, aldehyde has to be CHO, so aldehyde must be at the very end. If they don't give us information, I will just draw the simplest aldehyde, straight chain 4 carbons. So this thing is going to be CH3, CH2, CH2, CHO. Carbon form 4 bonds. If I only show 1 bond to carbons, there are 3 more hydrogen which are not shown. Carbon form 4 bond, 1, 2, so there are 2 hydrogen. Carbon form 4 bond, 1, 2, so there are 2 hydrogen. Carbon from 4 bond, 1, 2, 3, there's 1 hydrogen there. This is structural, this is skeletal. They want skeletal, we are not given the choice, we must draw skeletal. Now onto the other ones. This is a straight chained aldehyde, but of course you can see there are 3 carbon here, then you can branch out. This is very typical, when you have 3 carbons, you can branch out. Now you can have 1, 2, and 3. So this is now propanol, and this is 2-methyl propanol. This is going to be CH3, CH, bracket CH3, CHO. So that's the name there. We are not asked for the name, obviously, but you know, it's quite interesting if you think about what sort of things could be asked, obviously. And this first one there, they didn't ask for the name, but it's a 4-carbon aldehyde. This is just butanol. On to C, this one is ketone aldehyde, but it doesn't give you the brick red PPT, it doesn't give you the positive result with the phalanx reagent. So this must be a ketone. And we're looking at 4 carbon ketones, C4H8O. These are isomers, these are functional group isomer. Ketone and aldehydes have the same molecular formula, but different functional group here because they are functional group isomer, specifically coming under structural isomer. So 1, 2, 3, 4. You can of course draw the other way around, which is this way around. This is also 1, 2, 3, 4. Both of them will have the same name. It's called butanone. You can name it butane 2-on, but there is only one isomer. Butane 2-on is butanone. Now name the type of structural isomers shown by A and B. They didn't specify which one is A, which one is B, because they didn't mention which one is branch, which one is straight chain. This is very clearly open to interpretation. You could have gotten, you know, B as the straight chain or A as the branch chain. It doesn't matter because there's no other information to tell us what is A or B apart from 4-carbon aldehyde. And the relationship between the straight chain and the branch chain is called chain isomerism. It comes under structural isomerism. Just like the relationship of A with C or B with C is functional group isomerism, aldehyde, ketones. Now state what you would see, describe what you would see when A is one with toluenes. Toluenes reagent is basically silver +1, but it's got 2 ammonia. So it's a soluble complex, and we'll learn more about complex ions in A2 transition metals. So this is aqueous, this is colorless solution, If A contains aldehyde, aldehyde can be oxidized by toluenes, and then this silver +1 will go to silver 0, and you will see a silver mirror or silver precipitate forming. So typically, the best result that you will see is a silver mirror you will see a silver mirror forming. But sometimes you can get like a gray precipitate or a gray solid forming. There's also a result of the silver atoms getting produced or getting formed without forming the silver mirror, because experimental issues, sometimes you don't get a perfect silver mirror. Now we're talking about 4 carbon just now. I think C4H, C4H8, C4H8O. So when we look at C4H8O, we are not looking at aldehyde or ketones. So these are D, E, and F. They are not aldehyde, not ketones, because they did not give you the orange PPT with 2,4-D and pH. But they all decolorized bromine. If they all decolorized bromine, they must have carbon-carbon double bond. This is called test for unsaturation. Unsaturated stuff, they will add bromine onto the double bond, and therefore you will get decolorization of the bromine water from orange or from yellow-orange to colorless. Effervescence slowly with sodium metal. So this is with sodium metal, which is a reactive metal, and there is OH group. So are we sure that it could be carboxylic acid? Yes, but it could also be alcohol, because alcohol can react with sodium as well to give you hydrogen gas. Carboxylic acid can react with sodium to give you hydrogen gas as well. And what do we know? E shows geometric isomerisms. Geometric isomerism is your cis and trans. Only D has a branch chain. None of these isomers, none of them contain a oxygen atom bonded to a carbon atom involved in pi bond. So we are saying that we do not have this, nothing like this, none of these. So we have a carbon involved in pi bond, but we do not have any oxygen atom bonded to a carbon involved in this carbon-carbon double bond, which is a pi bond, 1 pi and 1 sigma bond there. None of these isomers contain a chiral center, none. So no chiral center, remember, yeah, no chiral center. Give the structures of D, E, and F, and you got to show the 2 stereoisomers. If you want to show the stereoisomers, you cannot write, cannot use structural isomer, because if you define stereoisomer, they have the same molecular formula, they have the same structural formula. So you cannot use structural formula to show the difference between cis and trans. It doesn't work. Must display at the carbon-carbon double bond to show the cis and the trans, and then of course label the stereoisomerism. What do we need? So we have 5 marks here. Let's try and draw this. So there are 4 carbons. D. If I just draw my double bond, and then is this doable? So there is 1, 2, 3, and 4. So there are 4 carbons, hydrogen, 1, 2, 3, 4, 5, 6, 7, 8. And then there is no oxygen directly bonded to that. But then D has a branch chain, so I can't branch it unless I remove this one and branch it there. So only then I can branch it. So perhaps I have this thing here like this, and then I just branch it there. So this is my branch chain, but I now have an issue, because you see this is chiral. You see how this one has a carbon bonded to CH3, OH, something with double bond, and then a hydrogen. So this cannot be the answer. This one is this one there. So cannot be. Cannot have a chiral center. Cannot be. So cannot be that answer. I wonder what else could it be. 4 carbons, and only E has cis and trans. So I'm okay here. How about this one? Wonder if this is alright. This is straight chain, so this is not branch. So let me see. If I have branch like this, so this one has no branch, so this one cannot be the answer, because this one is straight chained and you're looking for branch. I cannot have cis and trans, so this is a CH2. Both groups are the same on 1 carbon of the carbon-carbon double bond, so no geometric isomers for D. It has a branch chain, so this is the branch, There is no oxygen bonded to a carbon atom, which are involved in pi bond, so there is bonded on the next carbon. There is OH, so it does react with sodium metal, and I think D must be this one then. Okay, as for E and E, we are looking for the cis and trans isomer. So we cannot have this. All right, because there is no oxygen directly bonded to a carbon involved in the carbon-carbon double bond like that. So we must be looking at cis and trans like this, perhaps 1, 2, 3, 4, and then we are missing an OH, and the OH cannot be directly bonded to the carbon with a double bond, so it has to be bonded to the next carbon. I have drawn them to be the exact same thing because they are on the opposite side. So this is called the trans isomer. The cis isomer is not this one. I have to change this slightly, and this one will be the cis isomer, where the CH3 is on the same side as the CH2OH. On to F. What do we know about F? F has carbon-carbon double bond. F could be this. No, F cannot be this because this one contains chiral carbon. F does not have geometrical isomer. F must have OH group. F must have carbon-carbon double bond. I think F is possibly the straight chain. I think F is possibly this one because there is no chiral carbon. There is no branching here because they say only D has a branch chain and only D has a branch chain. There is no geometric isomer because only E shows geometric isomers, and then none of them contain chiral center, so it cannot be this, it must be this. Okay, hopefully that makes sense to you. When these alcohols react with sodium metal, and you get this alkoxide, so this is a giant ionic structure, and then you will give H2 gas, hydrogen molecule, but of course you only have one hydrogen atom to give away, so we must balance our equation no matter what. Identify the gas, it's going to be hydrogen gas, or you can write down H2 gas because they don't say about name or formula, but they did say if you write down the hydrogen gas, you have to write down H2 instead of hydrogen atoms. Now part C, this is about balancing equations. So we're going to use oxidizing agent is this square bracket O, which is counted as one oxygen atom, or this square bracket H for reducing agent like sodium borohydride. So we're given these molecular formula which are easier to balance, to be honest. We're going to react it with acidified potassium dichromate 6. So this is the orange color reagent, chromium plus 6, which is orange. You're supposed to be able to work out the oxidation number. -2 is the overall charge of the ion, equal to 2 chromium plus 7 times -2. So 2 chromium is -2 plus 14. 2 chromium is plus 12. So each chromium is plus 6. And then this orange color will go to chromium 3 plus, which is chromium plus 3, green in color. That is the positive result if it does act as an oxidizing agent because it oxidizes the alcohol here. Or is it alcohol? It's not alcohol actually. It says contain the same functional group as A. Contain the same functional group as A. What was A just now? A is aldehyde. So aldehyde can be oxidized to carboxylic acid. Aldehyde can be oxidized to carboxylic acid. So C3H6O, am I correct? So 3 carbons, 1, 2, and 3. CH3, CH2, CHO, 3, 4, 5, 6. So C3H6O. We're going to oxidize that. It's going to go to carboxylic acid. And then when it gets oxidized to carboxylic acid, we have CH3, CH2, CO2H, which is equal to 3 carbons, 3, 4, 5, 6 hydrogen, and O2. So C3H6O2. And this equation is balanced in terms of carbon. 6 hydrogen is 6 hydrogen, 1 oxygen plus 1 oxygen, 2 oxygen. This equation is balanced now. On to the next one, you have reducing agent. So the same thing, we're going to reduce aldehyde. And when we reduce aldehyde, we will get the primary alcohol. Running out of space there, but there's the primary alcohol. CH3, CH2, CH2OH. So there is a total of 3 carbons. And then 3, 4, 5, 6, 7, and 8 hydrogens and oxygen. So 6 hydrogen, 8 hydrogen. I need 2 hydrogen atoms in order to add up to 8 hydrogen. The oxygen and carbon are already balanced. And that's the end of that 13-mark organic question.